Thank you very much for this introduction. So the program today, lecture 2, is about inverse function theorems in the Banach setting first, and then in the Fréchet setting for Nash-Moser version. Here, the plan of the talk. First of all, we will see the Banach version of this theorem and its proof. Then we will introduce the Tame category in which the Nash-Moser version is valid. Then I will give you some toolkits to use this theorem easily, I hope. And then we go through the ideas of the Nash-Moser theorem of the proof. We'll see how much we can do there. And some application, very few. Let me make some advertisement for also the lecture for tomorrow. Tomorrow, we will see some pathologies in infinite dimensional geometry. I will introduce the toys we can play with, Riemannian structure, symplectic structure, any kind of geometric structures. Then I will give a list of traps in infinite dimensional geometry, sorry. Then I will give an example of a Poisson bracket, which is not given by a Poisson tensor. This will be on a Hilbert plate, so very, very easy manifold. At last, I will give tomorrow the definition and some application of Banach-Poisson-Lie groups. This is a paper that just appeared, a paper of mine that just appeared in Communication in Mathematical Physics. So I think I should make some advertisement here for this paper. Let's go on. So here we start with the Banach version and the Fréchet version of the inverse function theorem. Here the picture you see, it's just to have an idea how these proofs are built. There are three theorems playing a role here. First of all, the yellow one is a contraction theorem. This is at the basis of all these theorems. In the Banach setting, we use the contraction theorem to prove the inversion function theorem. So the inversion function theorem is the red brick here. So it is built, it's based on contraction theorem. On the other hand, in the Banach setting, we can prove the Cauchy theorem, which is a green brick here. So the Cauchy theorem also sits on the contraction theorem. This is in the Banach setting. And in the Fréchet setting, the bricks are built one up on the top of the other. So the Cauchy theorem enters the play in the proof of Nash-Moser theorem. And my goal today is to explain to you how Cauchy theorem enters the play and how it makes a proof of Nash-Moser theorem work. Two references: a Hamilton paper for all details, a small chapter in the book of Kriegel and Micho. There it's very dense, but every detail is also there. So in Hamilton paper, there's a lot of examples, and so the paper is very long. In the small chapter at the end of the book of Kriegel and Micho, it's just focused on the proof. Okay. Let's start in the Banach case. I recall, we saw it yet in lecture 1, but I recall it, the fixed point theorem or contraction theorem. So we are in a complete metric space. There is a contraction here. Is the contraction is denoted by F. Then we can, contraction means that the distance between two images is less or equal than a number k, which is less than 1, times the distances of the two initial points. And if it is the case, then there is a unique fixed point of this map. And the construction of this fixed point is the following. We use a sequence given by x sub n plus 1 equal to the image of x sub n. And this sequence converges to the fixed point. The proof is very easy. It's just the fact that this sequence is a Cauchy sequence, and we are in a complete metric space, so it will converge. And moreover, the limit is I mean, there is only one fixed point. There is uniqueness because of this condition that the map is a contraction. Okay, in more detail, if you want, for the students here, you can show that this sequence is indeed a Cauchy sequence. So you look at distances between two elements of the sequence, x sub n plus 1 and x sub n. And this is using the contraction condition, it's less or equal than the distance between the two previous points. And you go on like this until you reach the first one, the two first ones points, x1 and x dot. And here there is a k to the power n entering the play. And because k is less than 1, this is an element of a convergent sequence. And this makes all the things work. So you can have a bound on the distances between two different elements of the sequence. I think this should be clear. We go on. Now we want to address the Cauchy theorem in the Banach setting first. So I'm trying to prove, at least to give the ideas of the proof of the 3 bricks. So the yellow bricks is now behind us. We have this contraction theorem, just Cauchy sequence converging in a complete metric space. Now we are going to this green theorem, the Cauchy theorem. In the Banach case, well, this is a long text, but there is one main player here. It's a map P, which is a vector field. Vector field, it's a time, I would say, time-dependent vector field. So there is a t, a parallel to t entering one of the arguments. And this vector field lives on an open set of Banach space. So U is an open set of a Banach space. And it takes value in a Banach space. So it's a vector field depending on time on this Banach space defined in an open set. There are two conditions, two estimates on this vector field P. It is bounded, this first one, and it is Lipschitz. That's the second condition. If it is a case, then for any f dot in the open set U, we can find a neighborhood, a small neighborhood centered at f dot, sorry, small neighborhood centered at f dot, and an epsilon, which will give you the time, maximal time, where the Cauchy problem that I wrote here has a unique solution with the initial condition that the flow here of phi is a flow. The flow at time 0 should be for an element f at f. So this Cauchy problem has a unique solution. And yeah, moreover, the solution has the same regularity as P. I draw a picture because I think this needs a picture. So here is my picture. There is an open set U inside of a Banach space B. In this open set, there is a point F dot. Inside a neighborhood of F dot, which here will be a ball center at F dot with some radius R/2. If we start with an element F in this ball, then the flow will exist and it will stay in a bigger ball. That's the idea of the theorem. So more precisely, there will be a small ball in which the initial values will take place. And the flow can leave this small ball, but it will remain in a ball where all estimates are valid. Okay, so how do we prove this Cauchy theorem? So we have an equation. The Cauchy equation is that the derivative of the flow is equal to the vector field at time t and at point given by the flow. This is a equation. If we integrate with respect to time, using the initial condition that at time t we are at f at the point, then we get this condition that the flow at time t starting at f0 at time t0 is equal to f plus the integral of the vector field. Here you see that the flow appears at both sides of this equation. And this should tell you that this flows is a fixed point of a map. The flow on one side is equal to some function of the flow on the other side. More precisely, this flow is a fixed point of an operator S sub f, which is exactly the right-hand side of the equation. Okay. So now we want to find a space where this operator SF acts like a contraction in order to use the contraction theorem. And the contraction theorem will give us a fixed point of this operator. So now the metric space we are using is a space of continuous maps from an interval, a closed interval minus epsilon, with values in some ball. And the ball will be the big ball I drew before. There will be a radius that we have to fix. This space of continuous curves is a complete metric space for the distance which is given here, the subdistance, the distance between two function will be the supremum for all time of the differences. There should be a minus here of the distances between the element of the curve. Okay, so you have a complete metric space, and we want to find appropriate parameters epsilon and r, such that using the estimates of the hypothesis of the theorem, such that this operator SF is a contraction. So there are two conditions. The operator SF should preserve the space, and it should be a contraction on the space. That's the two ingredients for the contraction theorem. So here the first condition that this operator SF preserve the space It says that for any t, we are not leaving the ball of radius r center at f0. So we have to compare we have to evaluate the difference between this SF of a curve at time t and the point f0. And we want this to remain smaller than r. We want to preserve the ball of radius r. So here I'm just writing what's S sub f. This was the right-hand side of the equation. We use a triangular inequality very easily. For the first term, we get f minus f0. F will be the initial value. So the initial value should not be too far from f0. And then we have to integrate the vector field, P, but we have an estimate on the vector field. We know that it's bounded. So this we can estimate. Well, the time will be less than epsilon, so there is a epsilon, and there was a bound on the vector field, which was a constant c. So okay, so in order that this operator SF preserve the complete metric space we are dealing with, we need this red condition. This will give a condition on the initial value f, initial values. Okay. Second condition, this operator SF should be a contraction. Contraction means that we can estimate the distance between the images with the distance between the initial points. Here we are in a space of curves. The complete metric space we are dealing with is a space of curves defined on minus epsilon epsilon with values in some ball. So alpha and beta are curves. And here I just give the definition of what's the distance between two curves is. And now we have to estimate this and find a majoration with using the difference between alpha and beta. So here, here what will play the role, it will be the second estimate on the vector field. So we know that the vector field is Lipschitz. So instead of yes, first we put the norm inside the integral, okay? And now we use a Lipschitz estimate. So these values between P at alpha and P at beta is less or equal to C primes. This is a Lipschitz constant between alpha, the difference between alpha and beta. Okay, so here we have an estimate which says that the distance between two images of the curve alpha and beta through this operator SF is less than some product of constants, the distance between alpha and beta. So here we need that this constant, which is C prime times epsilon. Epsilon is a time interval. C prime is the Lipschitz constant. This should be strictly less than 1. That's the second condition. Okay, so at the end we have two conditions, these two red conditions, and we have to choose a constant in order to make this two condition works. So if I don't made mistakes, well, the constant C and C prime, you can take them greater than 1. And then you take for the initial collision F, that there are f minus, that the initial condition f should be in the smaller ball of radius r/2, and the time should be less than r/2c prime, and r should be less than 2c, and such that no integral curve leaves the domain. So I give you an exercise for tonight. We have a discussion at 6. Make this work. Can you check that this work indeed, please? Okay, now there is a theorem, Cauchy theorem in the Fréchet setting. And more or less, it's an adaptation of the Banach case, because it's valid only for maps which factor through a Banach space. More precisely, here we have, there is a typo here, I see it's a 2 here. We have a smooth map between Fréchet spaces. First one is F1, the second one is F2 and not F1. And this map is called a smooth Banach map if we can insert a Banach space in between, a Banach space B, such that this map P is the composition of 2 maps, Q and R. R is going from the first Fréchet space, actually an open set of a Fréchet space F1, to an open set of a Banach space B. And the second one, Q, is going from this open set of B in B to the second Fréchet space. So we have a map which is decomposed into 2 blocks. In between, there is a Banach space. And this map is the vector field on the Fréchet space F1 we are wanting to integrate. So here the Cauchy theorem in the Fréchet case, we have a map P. So now there's only one Fréchet space. The map P is a vector field defined on an open set U of this Fréchet space. The condition is that it's a Banach map, so it can be written as a composition of 2 maps with a Banach space entering the play. And it's mapped Fréchet space into itself. Then, if you take for any F0 in this open set, we can find a neighborhood of F0 and a time interval of size epsilon, such that for any initial value in this smaller neighborhood, the differential equation df over dt is equal to pf, has a unique solution with initial condition given by f0 is equal to f, and the time interval is fixed, epsilon is fixed, and the solution depends smoothly on t and f. Okay, so there are some differences in comparison to the Banach case. Here, the map P is supposed to be smooth, and a Banach map.
So maybe, Barbara, there are precisely over this condition, there are a couple of questions in the chat that I think they ask similar thing.
Okay.
They ask about the factorization. What does it really mean? And basically, if it is always possible to insert such Banach space.
Oh, no, it's not always possible. It's no, not every map is a smooth Banach map. Not every map. So it's very particular, but it turns out that there are a lot of examples of this, and Yes, and the Nash-Moser theorem uses this, exactly this. So there will be Banach spaces entering the play in the Nash-Moser theorem.
Actually, it was saying not about the map. I think
But-
he meant if you can insert the space. Wait, what?
Can I talk?
Sure. Yeah, please talk.
I would just know if I can always find such a map for two Fréchet spaces, and so I can find a Banach space to insert between them. So I have two Fréchet spaces, but yes. Can I always find the a map and a Banach space that I can insert between them, or there are some condition on
the Fréchet spaces?
Yeah,
I don't know.
Okay.
Okay, I don't know. I don't know.
Thanks.
For the Cauchy theorem, first we have only one Fréchet space, and yes, the map P is supposed to have this condition. So there may be some restriction on the Fréchet space. And yeah. But we will see then a bit later the Tame category, so it perhaps will answer the question.
Okay, because I think there is also a couple of other things still on this topic. So first, Andrew was also asking before what this factorization really mean. I don't know if you want to explain a bit what you meant.
Can I try to clarify?
Yeah, sure, please.
Yeah. So I guess what I mean is this really describing some interesting class of mappings that can be factored like this, or is this kind of a separate condition that's not related to any other condition about, say, general continuous or general mappings between Fréchet spaces?
How restrictive is this condition? That's a question, huh?
Yeah, or is there sort of a big framework in which this is an interesting sort of special case of a certain class of mappings or something like that?
Well, in the same category, I think that there will be a lot of map like this.
Okay. Maybe it'll become clearer when we talk about it.
Yes, I think so. I hope. Okay, let's go on.
Yeah, yes? I think there was a very last one. Probably the answer is a yes or no. Given the map, is this Banach space factor unique or not?
No.
Okay.
Okay, let's go on.
Okay, thank you.
Thank you for your questions. Okay, so here we adapt the proof in the Banach setting by modifying, in fact, the operator S sub F that I wrote before. So the operator that gives a fixed point, because we wanted to go from Banach space to a Banach space. So the Banach space B will play the role here, and the factorization also. So let me, so this K is in fact the analog of SF before. So this is an operator acting on a space of maps. Q is going from a Banach space to the Fréchet space F, and R is going from the Fréchet space to the Banach space. So if you look at Q of F, this takes value in a Fréchet space, and then you go back with R, and you end up with in the Banach space. So this map is going from the Banach space into itself. Okay, so now we have a map from a Banach space into itself, and we are doing the same thing as before. We should find a complete metric space stabilized by this map and on which it is a contraction. That's the idea. Okay. Okay, so now we have another brick, which is the red brick in the Banach setting. The inverse function theorem in a Banach setting. So here, here the theorem. We have a function on an open set of a Banach space B1 with values in another Banach space B2. It's supposed to be C1. And the condition also is that it is the derivative of this map is invertible at some point A of this open set. And the conclusion of the theorem is that locally F is a C1 diffeomorphism. So there are neighborhood V of A, so a neighborhood of A and a neighborhood of its image on which F is a C1 diffeomorphism. Moreover, we can replace here C1 by CK or C infinity. Okay, so now we will go through the proof of the theorem. There are some steps. The first one is reduction, so normalization, in fact. For this, instead of F, we will normalize the map in order to, the point A should be 0 and its image should be 0. So we go to, the map should send 0 to 0. So that's one normalization. And the differential of this map at 0 should be the identity. We can do that using the open mapping theorem. Why? Because we know that the differential of F at point A is invertible. And it is continuous by assumption also, because the map F is C1. It's invertible continuous, so its inverse is also continuous. So here I use this inverse. And it is also continuous. So the map that we get here, I call it J, but I'm not sure if I maintain this notation afterwards. Anyway, we subtract the value of FA and we apply this, the inverse of the differential, and we end up with a map sending 0 to 0 as such that the differential of this map at 0 is the identity. Okay, so this will simplify the notation afterwards. So now we have a map sending 0 to 0 with differential equal to identity at 0. Okay, now we will use the contraction theorem to prove that it's a bijection. And then we will see step 3, 4, 5 that the reciprocal map is smooth. Okay, so now here we want to find the solution of g of x equal to y. Y is fixed and we are looking for a preimage x. We want to solve this as a fixed point of an equation u sub y of x is equal to x, where this map is given by a formula here. So y is a fixed element such that we are looking for its preimage. And so u sub y applied to x is equal to y minus gx plus x. For y equal to 0, we get another map, which is called u here. And we see that because the differential of g at 0 is the identity, the differential of u at 0 is 0. And this is good because we are on the Banach space, and all the map are C1. So there's this operator norm of du. We know that at 0, du is 0. So in a neighborhood, the norm of du of x is less than, say, 1/2. So there is a small neighborhood, a small radius r, such that it should be 0, a positive radius, such that for any point of this ball, center at 0 and radius r, the differential, the operator norm of the differential of u is less than 1/2. Okay, so we feel that it will contract. We put ourselves in a situation where there will be some contraction. We take some constant less than 1 here. Okay, so now we want to see that G is a bijection between two balls, a center at 0, a big one which is of radius r, and the smaller one which is of radius r/2. And for any y in the small one, we have to find an x in the big one, satisfying that the image of x is y. Here, we use the fact that this equation, image of x is equal to y, can be written as a fixed point equation for the map u sub y. And now we have to verify that this function u sub y is indeed a contraction on sorry, I'm just trying to read. So we use, first of all, we use the majoration here. So we want to see that the ball of radius r is preserved by u sub y, by the map. The ball of radius r is preserved, and it is on a contraction. So u sub y of x should be in norm less than r. Here we use a triangular inequality. First, triangular inequality, and then second we use the mean value theorem, because we have a estimate on the differential of u. So the norm of u of x is less than 1/2. This was a constant we took, times the norm of x. And we want, and this is less than r if the norm of x is less than r. So the ball of radius r is preserved. And more or less, the function u sub y is a contraction there. So here we have to estimate the difference between the images, two images. And again, we simplify because it's the same y here, so there's no y entering now in this difference. And again, we use the fact that the differential of u is in norm less than 1/2, and we get this contraction estimate. Okay, so now we have this bijection, and this gives us this inverse map. We have to enter also that this inverse map is continuous. In fact, it is Lipschitz with constant 2. This is only a triangular inequality, so I will be a bit faster here. And then we have to show that this inverse is differentiable. So for this, we need the open mapping theorem. And we have to estimate in this that it's here the first order Taylor theory, that this is small. And for this, we're just using that if we take the differential of G at some point X, then it is invertible by hypothesis, and it is continuous because of the open mapping theorem. So we use it to make some estimates. Okay, this is a bit too long. I'm looking at the time, so I should skip this. And then you have to check that the derivative is continuous. So I'll skip this also. Okay. So why this is not working in the Fréchet context? The theorem I mentioned, contraction theorem, is okay because the Fréchet space is complete metric space. So this is okay. The open mapping theorem is also okay. It's even valid in a more general setting. The mean value theorem, well, you can replace it by a Taylor expansion. That's also okay. We have seen the Taylor expansion makes sense in the Fréchet context. So what's not working? So here I have an example where the derivative at one point is the identity, but the map is not in the derivative is not even injective at points in a neighborhood of 0. So here the example is the exponential map from the set of vector field on the circle with values in the group of diffeomorphism of the circle. This is given by the flow of the Cauchy problem. We have a vector field of S1. We took the constant vector field. We took the flow of this vector field. We stop at time t equal to 1, and this gives us a diffeomorphism. This is exactly this map exp. At 0, the differential of this map is the identity because it's exactly the vector field. But there are vector fields which are arbitrarily close to 0, such that the differential of this exponential map is not injective. So here the example is the following. So this vector field are constant vector field with given rotation. I draw them here. So constant vector field on the circle with velocity such that if you rotate the circle at time t equal to 1, you have a rotation of angle 2p over k. Okay, constant vector field with a small velocity. For notation, phi z will denote a flow, okay, on this manifold S1. So here the idea, we want to differentiate. We want to see that the differential at this point, at this vector field x 2 pi over k is not injective. So I don't know if my drawing is good, but we have to differentiate the exponential map at some x. So we take some perturbation and we see where this exponential map maps this perturbation. and we differentiate. So more precisely, we take the flow of x plus a perturbation sy. This is a flow. And we have to differentiate with respect to s. So we make variation of x. So we should differentiate at s equal to 0. And we differentiate with respect to t. Okay, so now we flip the two differentiations, and by definition, this is the map phi is a flow, so we know what the vector field is just x plus sy, and when we take a constant vector field, which will be our rotation vector field, then we make the computation. Okay, I have no time to do through this, unfortunately. And we get that the differential is some integral of the perturbation y. And now we have the choice of y. And the choice, a good choice, is to take some sinus of kx. And so because we have to integrate until time t equal to 1 to get the exponential map. And this cancel out because because of the sign property. Okay, so now the conclusion is that with this constant vector field given rotation, which can be as small as we want, there are directions given by these sign functions such that the differential is 0 in this direction. Okay, so this contradicts the inverse function theorem in the Fréchet context. Moreover, it is not even sufficient that if the derivative is invertible in a neighborhood, this will not be sufficient neither. So here the example is the map which to f assign exponential f. F is a smooth function on R. Well, the image of this function is we take exponential of function, so it's strictly positive. So there's function in the space of smooth function over R which are not positive, and this can be as close as 0 that we want. For instance, here C of S is a smooth path which goes through 0, and which is such that the image of this path is not given by a strictly positive function. At some point, the function is negative. Okay, but the map, if we want to differentiate this map, the differential is just multiplication by exponential of f, which is invertible. So here we have an example of a smooth map such that the differential is invertible and even smooth, but the map itself is not locally surjective. The image of this map E is contains only strictly positive functions, and so it's not surjective. Okay. Okay, so now we go to Nash-Moser theorem. I have to be very quick now, sorry. Okay, so what is it? Nash-Moser theorem, we have a smooth Tame, I will explain what it is, a smooth Tame map between Fréchet spaces. And now we impose that the differential is invertible in a neighborhood. So the equation given by dp of f applied to h is equal to h has a unique solution for any f in a neighborhood and any k in the Fréchet space. And the family of inverses, I call them L, is also a smooth Tame map. Then P is locally invertible. So here we impose invertibility in a neighborhood and some Tame condition. So we have to explain what Tame means. There are 4 notions we have to go through: graded Fréchet spaces, Tame linear maps, Tame Fréchet spaces, and Tame maps. A graded Fréchet space, it's very easy. It's a Fréchet space together with a collection of semi-norms with increasing strengths. So there is an increasing sequence of norms, of semi-norms. The prototype, and this is very important for the proof, actually the proof of Nash-Moser theorem will be in this Fréchet space, particular Fréchet space. It's a Fréchet space of exponentially decreasing element in a Banach space B. We denote it by sigma B. B is a Banach space, and the sigma B is exactly an example of a graded Fréchet space. For the norm which are given here, there is a sum with some exponential of some arguments. So these are exponentially decreasing sequences in a Banach space B. This is a prototype of a Tame, of a graded Fréchet space. Now, what is a Tame linear map? It's a linear map which satisfies some Tame estimate. So here we have on a graded Fréchet space, we have the sequence of estimate, and here the condition that is that we have an estimate at order n using the norm at order n plus r, and r is fixed. And this should be valid for n greater than b. B is a base. So at some point for n greater than a fixed number b, we have estimates using a shift of r on the norms. Okay, so a Tame map is exactly, a linear Tame map is a map satisfying this Tame estimate. For instance, I give here a Tame map, which is applies sequence to another sequence with some exponential in between, and this is an example of this, just a shift of indices. What is a Tame Fréchet space? A Tame Fréchet space is a direct summand of this sigma B for some Banach space B. So here I wrote what exactly this means. Tame direct summand, then it means that you have 2 maps, L and M, projection, surjection. The composition of it is the identity, ML is the identity. Okay, so this is for Tame direct summand, and we are interested in Tame Fréchet spaces. Here, a Tame Fréchet space is a direct summand in some space sigma B of exponentially decreasing sequences. So we have a block in some exponentially decreasing sequences. Okay. What is a Tame map? A Tame map is a map which goes from one graded Fréchet space into another one and satisfies some Tame estimates. And it is supposed to be continuous also. So here an example, taking f and taking the exponential f is a Tame map between the space of smooth mappings on an interval AB. Okay, so the Tame category is given by Tame spaces and Tame smooth maps. Okay, so now the Nash-Moser theorem is proved in this category, so I go through it. Before giving some ideas of the proof, I have 2 minutes, but I know I will be late. I want to give you a toolkit for using this theorem. So, properties of Tame maps. The composition of Tame maps is Tame. Continuous map of some graded Fréchet space into a Banach space is Tame. Any continuous map from a finite dimensional space into a Fréchet space is Tame. Any nonlinear partial differential equation operator is Tame between the sections, smooth sections of a compact manifold. And now we can build new Tame spaces using spaces that we know they are Tame. So the Tame direct summand of a Tame space is Tame. Cartesian product of two Tame spaces is Tame. And I'll give some list of Tame spaces, so we can then build other Tame spaces using this list. If X is a compact manifold, well, the smooth section, the smooth function on X is Tame. Even if the manifold X is with boundary, the smooth function on X is Tame. If we have a vector bundle V over a compact manifold, then the space of section, or smooth section of this vector field is also Tame. So functions, smooth sections are Tame. If we have a compact manifold and a fiber bundle, the smooth section of the fiber bundle is Tame. If we have a compact manifold and a finite dimensional manifold, the space of maps between these two manifolds is Tame. And the space of all smooth manifold of a finite dimensional manifold is also Tame. So we have a list of Tame spaces, and then we can build other Tame spaces using this. I'll give also a list of Tame Lie groups. The group of diffeomorphism of a compact manifold is Tame. The group of volume-preserving diffeomorphism of a compact manifold is Tame. I give a reference for this second statement. And here again, the Nash-Moser theorem. Okay, so I have, give me 5 minutes to go. I just want to.
We started also a few minutes late, so
okay.
We will postpone the question into this.
I will go through exactly to the point. So, in the Nash-Moser proof, it starts also with a normalization. The normalization is, first of all, we do what is needed, such that this the Fréchet spaces were on are these prototypes, sigma of B. B is some Banach space, but yes, in the hypothesis, we know that the Fréchet spaces are Tame, so they are a Tame direct summand of some sigma B. And so what we do is we extend everything to this sigma B, and that's where we will work. We do what is needed such that the map maps 0 to 0. And also we have estimates on this map because in the hypothesis of the theorem, there are the map are supposed to be Tame. Tame is saying that they are satisfying some estimates. So we can modify a bit these maps such that we we control these estimates. So for this, we use, it's here downstairs, an operator which multiply the sequence of the exponential decrease in sequence by some exponential, and using, well, we can manage to normalize these estimates. Okay, that's not so difficult. Injectivity is also not difficult. More or less, we use the Taylor formula and triangular inequality. Okay, so I will go far here. Oh yes, there is a new ingredient enter into the play, because now we know that we are on sigma b, on the space of exponentially decreasing sequences in some Banach space B. On this space, we can really compute, because we know the norms, we know the space. So here there is a interpolation formula that we have to check, but this this can be done. This is not difficult. And okay, this interpolation formula enters the play for the injectivity, and otherwise it's just triangular inequalities. Okay, now subjectivity, that's the main point. Okay, so here, that's where Cauchy theorem enters the play. Here to so we have normalized a map such that 0 is mapped to 0. Now we want to invert this map P. We want to invert it, so we want to find a preimage of an element G. We want to find a preimage of G. G is fixed. To do so, we will draw the linear path between 0 and G, which will be written like this. HG is as dilatation, is HT of G. Actually, we can make it more precise. This path will, when T is going to infinity, we will reach G. When T is going to infinity, we will reach G. So here the H is of the form 1 minus exponential of minus some constancy time T. Okay, and now we want to understand what kind of differential equation is satisfied by Ft. So let me be more precise. We are considering a linear path. T is mapped to Ht of G. Ht is given by this formula, and we are looking at a path satisfying that the image of the image of Ft is exactly Ht of G. So the image of the path we are looking for is this linear one. What kind of differential equation is satisfied by F? That's a question. So we have to differentiate this condition. And after differentiation, the differential of P is entering here. So the differential of P at Ft applied to F prime of T is equal to H prime of T times G. Okay. Here H is given, so we can compute H prime. And so we end up with this differential equation here. And now ht of g, this is p of ft here. So we end up with a differential equation on f. So in blue, you see where f is entering play. And that's where Cauchy theorem is useful, because we have a differential equation here. Now to use this Cauchy theorem, we have to go back to some Banach space. And so instead of solving the differential equation we are interested in, we use some smoothing operator, which will write this differential equation in some Banach space. So we approximate this equation by some equation on Banach spaces. And Banach spaces, well, is by normalization, we were in this Banach space of exponentially decreasing sequences. So the Banach space will be, we put 0 for indices greater than t. So then we get the Banach space because we have only a finite number of indices. So this is mainly the Banach space to the power t, or something like that, for t integer. And these are the Banach spaces we use to solve the equations. Okay, so then last part is to show that the inverse map is smooth, but that mainly like in the Banach setting. Now I'll give you just two application. I'm sorry, I have to go very fast. So in the space of plane curve, an example, really easy example of Tame manifold and where this Nash-Moser theorem can be applied in a very easy way. So mainly using the toolkits I gave before. We are looking at continuous map of length 1. Inside of these, there are arc length parametrized maps. And if you look at this space of arc length parametrized maps, this is actually a submanifold of the space of length 1 maps. And to prove this, we use a Nash-Moser theorem in an easy way. And moreover, there is the group of diffeomorphism, which is also a Tame Fréchet group acting on this space of curve, and this action is even Tame. Okay, so this is just to say that using just a toolkit, we can prove this kind of things. It's an example, a school example of application of Nash-Moser theorem, not very difficult. And there is a reference where we do something else, but this with my collaborator Steve Preston, we were computing some elastic metric, and then we saw that this was not proven in the literature. That's a space of arc length parametrized curve is a smooth manifold in the space of all curves. So we had to prove it. And here is my last slide, another application of Nash-Moser theorem. This one is not so easy. For rigidity of group action. So here the story is that when you want to know if two actions are conjugates, and so if you want, so for those who knows, Nash-Moser theorem is used from going from infinitesimal rigidity to rigidity. So when we have a rigidity at the tangent spaces of a manifold and want to go to manifold. Okay, I'll give you some references. I know I'm late, so yes, I stop here. Sorry, I was not So clear perhaps at some points, but it's hard in 1 hour.